Okay, so let's talk about Julia. I want to start a little bit at the beginning. What kind of is the motivation? How did Julia come about? And so this is just a bit of my popularization of what was kind of happening. So basically you had a bunch of scientists that were having a conversation that was kind of going over some time in the abstract. And their issue was that they didn't like the languages they were using, like Fortran, C and C++. These were the languages they used to get kind of high enough performance for the kind of things that they were doing. But it's not something that they really enjoyed using. And so the solution has been for many years to use something more kind of fun, productive, and dynamic like Python, R, MATLAB, and so on. Of course, the problem with these languages is that they're very slow. So this has kind of been the typical approach that people use. They use statically typed languages to create modules or parts in their solution that has to be high performance or optimized. So they've kind of been using two languages, which is why we got what we call the two language problem, that you have to kind of juggle these two different languages at all times. Maybe you have to write a module in this high performance language, or you have to rewrite the solution that you have prototyped in something like Python or R or MATLAB. So the general consensus is that languages have to be statically typed to get performance. But what if you could have a language that was dynamically typed language like Python that was also fast? Now, this is not something that people really generally believe is possible. I find that people aren't necessarily taking that as a serious proposition. But the Julia guys, Stefan Karpinski, Will Shaw, Jeff Zanzon, and Professor Alan Edelman, they've proven people are wrong on the issue. What they found was that if you let your language behave like a static language whenever possible, it's actually possible to get the kind of performance you get in these statically typed high performance languages. So what specifically we mean by that? Well, what I mean is that what they did was they analyzed all the source code of a lot of dynamic languages to see how the languages were being used. And what they found was that in 90% of the cases, or 90% of what the program was doing, it was actually operating in a kind of a static fashion. It wasn't using the dynamic features. So the dynamic features of the language is really only used 10% of the time. So their thought was, well, what if we can design the language so it's possible for a just-in-time compiler to treat the code as if it was static most of the time. So what kind of language is Julia? It's a general purpose programming language, dynamically typed, high performance, just-in-time compiled. And it's multi-platform and a numerical language. Now, some of these things sound like a contradiction. How can it be general purpose and a numerical language? What we mean by that is that it's been designed so that they're trying to avoid to have it a special purpose language, kind of like MATLAB and R, which are mainly just used for science. They wanted to be more in the kind of Python, Ruby kind of category where you can use it to create a web page or a Unix tool, or almost whatever you want. But unlike those languages, they've added special features that make it a good numerical language. And what we mean by that is that you have things like NumPy, so the ability to work with large number of values, like in arrays, multidimensional arrays, matrices. Those kind of things are kind of built into the language, not built in specifically as part of the syntax, but they made constructs in the language that allow you to implement these kind of things in a natural fashion. The other thing is that it has very first-class support for numbers. So in Julia, numbers exist in this kind of rich type hierarchy where you can have abstract number types, signed numbers, unsigned numbers. You don't necessarily need to specify what the bit length is. You can add your own particular number types. If you come up with a new floating point number with a new definition, you could add that to Julia. Now I say that it's a just-in-time compiled language, and people have probably heard about these kind of languages before. Like you have JavaScript using the V8 just-in-time compiler, which is pretty high performance. But it's important to note that Julia just-in-time compiler is a very different kind of thing. JavaScript, and you have, for those who use Python, you might know PyPy, which is a just-in-time compiler for Python. These are what we call tracing JIT compilers, and Julia uses what we call a method JIT compiler, which is quite different. It's actually a much simpler compiler, but we're going to get more into that later. So the next thing that pops up when I discuss Julia with people want to know, oh, what's a big well-known application that's implemented in Julia that I have used potentially, on my phone or on a website or something. But at this moment, Julia is not, it's a fairly new language, it's about 2 years old, so it's not really reaching that kind of usage. But that doesn't mean that it's not used for serious work. But it's just that currently, if you're looking for where Julia is kind of used in a big way, you're going to find it on supercomputers. So you have things like the Celeste project, for instance, which is processing 178 terabytes of data of celestial objects, so planets and stars and so on, and trying to categorize them, creating a catalog for astronomers to use. So this is running on 650,000 cores. And I believe Julia is the only dynamic language that runs on supercomputers. And there aren't that many languages in general that are being used in supercomputers. Now, it's a little bit wrong of me to say that this is typically what Julia runs on. Obviously, this is being used a lot by scientists that are doing analysis of data. So data scientists, machine learning experts, and so on. But the point is they're not typically creating end user applications that you're running on your phone or in your web page. Another example of places where Julia is used is the next generation climate model is being developed on Julia. And this is not just some bunch of geeks that are doing this. Is scientists at Caltech, Massachusetts Institute of Technology, NASA Jet Propulsion Laboratory. So these are people at the leading edge in this field. And this is all open source, so you can actually look at it at GitHub. But they picked Julia a couple of years ago, and they did a kind of bake-off test where they tried different languages. And back then they found that Julia was only a few percentage points away from Fortran in performance. And that's quite remarkable. Usually if you have seen comparisons of performance, you will find that Fortran typically has been the lead above C actually in kind of numerical performance. And Julia got only a few percentage points away from that. And in fact, there has been climate models that people have built that are when they switched to Julia, they were kind of, their aim was to be about 30% of performance of what they used to have, because they wanted a more productive language and they were willing to take a performance hit to do that. But it's actually, in one of these cases, the researchers ended up with 3 times the performance of what they had before. So actually today, what we're seeing is that in many cases, Julia is actually offering higher performance than what you get with Fortran, which is quite remarkable for a high productivity, high level dynamic language. Now, Julia is not used only for science, of course. You can also do other things. So you have, for instance, the Genie Julia framework, which is The equivalent of Flask, Django, Ruby on Rails is not widely used yet, but I think that this is something you'll see increased usage of as Julia becomes more popular. So just a reminder, if people have questions, I'm not following the chat window at the moment, but I do follow the Q&A window. So if you have any questions, you can post them there, and I'll speak them out and try to answer them. But of course, we'll have some time to discuss things after we've gone through everything. But if there's something that's unclear, then please just ask a question. So what does Julia actually look like? This is an example from a training that I do. It's actually on the 13th of April this year. I'm doing Julia training through 60 North, which is the company I work for. So as you can see, Julia is not these kind of well-known curly braces programming languages. And it might look a little bit weird for some people, but actually the syntax is actually used in a number of other languages. So you have, for instance, Lua. If anyone has done kind of like game programming, they might be actually quite familiar with the syntax. And then MATLAB has similar kinds of syntax. And you actually find this in kind of these older, like Pascal, Algol, and Ada has similar kinds of keyword usage. So this isn't entirely invented by Julia. So you see that you have while, end, if, and. So these are kind of how you mark the beginning and the end of coding blocks in Julia. One thing that's a bit different from Julia from other dynamic languages is that we do use a fair amount of type annotations. So I highlighted those in blue here. You can see the spaceship argument is a type space vehicle. The delta T is a type number. And here it comes as sort of like numerical aspect of Julia in where you can work with abstract number types. So a int 8, for instance, an 8-bit integer is also a number, but you don't have to necessarily specify the bit type. Another thing you see is that we're using a Greek letter delta. Julia is all Unicode, and it's because it's used a lot by mathematicians that use Greek letters in their equations. Julia has very good support for using that. So your typical Julia editor or IDE or your interactive environments has very good support for adding these kind of symbols. And you notice you have the text string describing the function at the top here, which is similar to what you would do in Python to document functions. So let me go through a little bit of the topics that I'm going to cover. So one of the things I really want to get into is what it is that makes Julia so fast, because I think this is something that people don't quite understand why, and I think is also kind of interesting thing because the interesting technology choices there. But to be able to do that, I first have to do a bit of a language tour, give you a bit of sense of what the language is like. And then I'm going to talk about, in programming language trade-offs, I'll talk a bit about what are the trade-offs you typically do in a programming language. So what is it that makes a dynamic language typically slow? And then we'll get into what actually is the secret sauce. What is it that Julia does that these other languages it doesn't do that makes it so fast? And then we get further into the details by looking at how Julia actually does JIT code generation, because this is actually quite different from other JIT compilers. And in many ways, what's interesting about this is a lot simpler actually than something like JavaScript. I can't imagine that I would have a talk about JavaScript and talk about how it JIT compiles. Maybe I would. I don't know JavaScript enough, but that's not my impression. And finally, I'll have a bit of talk about the expressiveness of the language, because it's fine if you have a high performance language, but the whole idea of Julia, right, is that you can have the kind of productivity that you're used to from other dynamic languages combined with high performance. I want to show you that you're not losing any kind of expressiveness or productivity by using Julia. So a central thing in Julia is the Julia read, evaluate, print loop, the REPL. So it looks like this. You can start off from the command line. You can type something, hit enter, and it evaluates and it prints out the result. So here I wrote 2 + 4 and I got 6 as the result. So I'm going to show you a lot of the kind of examples of interactions of this kind through the talk, because this is how we would typically learn Julia and work with it daily. So here's an example of a hello world in Julia, and I just added some Chinese characters to show that Julia it's all Unicode. You can use Chinese, Greek, whatever you like. I'm going to go through a little bit of the language features. I'm not going to be able to cover everything, but I think it's useful to look at composite types, because there's a bit of a difference here compared to other dynamic languages. And then added Python and C and C++ here. Fortunately, a lot of you guys know these languages. And the reason why this is interesting is that while Julia is a dynamic language, you can see that the way you define a type in Julia, a composite type, is much more similar to C and C++. You can see things are swapped a bit around. I marked the type information here in blue. And you can see that we have swapped those around in Julia relative to C and C++. But other than that, the structure looks very similar. You can compare it with Python. For those of you who don't know Python, this underscore init method is what's being called by the constructor to initialize a newly created object in Python. And in Python, as in most other dynamic languages, you create the fields in the objects on the fly. So here we're creating name, health, and armor on the fly. Let's see, a little moment here. So the but in Julia we list up all the elements. But one thing that's nice is that kind of like C++, you get a constructor for free. So if I create Sir Lancelot, the White Knight, I get some nice kind of constructor that I can use that just follows the sequence that I defined the elements in. And Julia also gives me a sort of pretty printing or textual representation of what I created. And this is pretty nice because most languages you would have to kind of define these things yourself. So in Julia, it's very easy to just start working with objects and be able to sort of look at the values of the objects that you're working on interactively. We have the dot notation that allows us to access individual fields, like getting the health of Sir Lancelot. Now, this might look a lot like statically typed languages, but I want to show you that under the hood, this is very dynamic, everything that happens. So if we create the Black Knight, Sir Morian, you can see that we can access his name like this. But this is actually syntactic sugar for a function call. So what actually happens is this turns into get field, and the second argument says which field that we want to access, and that's basically like a string. Not quite a string. That's why we see the colon in front, which means that it's a symbol for people who use Ruby or Lisp or Scheme or something like that. Might be used to that. Otherwise, you can just think about that as an immutable string. So that means that you can get this value anywhere from. You can get internet from a user, from disk, and you can use that to dynamically look up a name without a compiler knowing ahead of time. So this would be something that you wouldn't really be able to do in C++ because the names of the fields don't really exist at runtime. only at compilation time. You can also access the fields by an index. So I can say I get the third field, for instance, which is that's the armor, which is 2. So let's look a bit at loops. Not that special or different from other languages, I guess. This is looping over an array of 3 elements. I highlighted the array here we're looping over. One thing, though, that's a bit interesting is working with ranges. In a lot of languages, you can see this is our range from 3 to 5. In a lot of languages, this would be part of the syntax for the for loop. In Julia, it's not. In Julia, the colon is just an operator that creates a range object. So you can do that separately. I can create a range object and put it inside a range variable, and then later I can iterate over it. So really, the only thing that the Julia for loop cares about is that it gets some kind of iterable object. And that applies to a lot of functions in Julia. So if you have, for instance, the sum function that adds up all the elements that you supply, it typically just works on something that you can iterate over. So you can add up all the elements in an array or add up the elements in a range. And of course, you can make these kind of functions yourself. They don't have to be built in. If statements are also a little bit different. It looks maybe a bit weird here that you're not actually doing anything in each of the cases. There's just a string there. So what's going on? Well, that's because in Julia, if statements are expressions. So if you're familiar with this from languages like C++, I think is also in Java, you have this unary operator, the question mark, that allows you to return the value in a kind of if statement. So Julia if statements work basically like that. So if the x is larger than 1,000, then the s will get the value large. Otherwise, it will get small. So everything in Julia is an expression that can get evaluated. So this is very similar to very functional languages. Functional languages tend to work this way. Everything is an expression. And because there's this big focus on functions in Julia, and we want to be able, and it's intended to be good for doing scientific things, they made it very easy to write one-line functions. And so I find also personally, I write a lot of one-line functions in Julia because they're just so easy to use. And the interesting thing about Julia is writing lots of small functions. This actually gives you higher performance in Julia than writing lots of really large functions. And this is kind of opposite about how things typically tend to be. People might actually want to write a larger function to avoid the overhead of calling a function. In Julia, it's the opposite. You want to do small functions if you want to have higher performance. So, of course, you write whatever natural size for you, but there's no downside to writing lots of functions. If you want multiple lines, you will have to use the function and end keyword, so you can mark the beginning and the end of the code. And here you can notice that I also added these function annotations. So here it says that the arguments, the x and the y, are of int type. This is actually shorthand for a 64-bit integer. If I wanted the sort of more generic integer, I would have to actually spell out integer completely. So this is an example of calling these functions in Julia. So let's look at dictionaries. I'm going to give an example of using these dictionaries here. So this is for creating a dictionary with these two keys, 2 and 4, and the mapping to the corresponding integer. So you can do that in different ways. Here it's easy to think that the rocket symbol, that I marked here in purple, that's somehow built in and special for a dictionary. And again, this is really just like the colon. It's just an operator or a function in Julia that creates a pair. So you can do that separately, you can put a list of pairs into an array, and then you can create a dictionary from that. It doesn't even need to be a pair. It could also be tuples that have 2 values. So this is a list of tuples. You can also use that to create a dictionary. You can have 2 separate arrays, and you can zip them together to create pairs in one single array and create a dictionary out of that. Using a dictionary should be pretty familiar to people. It's noticeable that you get this pretty print, so you can always see what's inside your dictionary. And notice that you have these curly braces here, which is where Julia provides a type arguments. So this says the type parameter, sorry. So this says that the key is a type string and the value is a 64-bit integer. So Julia just derived that from looking at what you provided it. So we can access individual elements, set them in a kind of normal fashion. You can see they get updated now. So let's look at a bit more functional style of programming. This is, of course, a big part of Julia. You can do sort of object-oriented programming in Julia, but it's more geared towards a more functional way of thinking. It's not a pure functional language like something like Haskell or OCaml. It's trying to be pragmatic. So here we define a square function, and if you looked a bit at functional programming in different languages before, you should probably be familiar with a map function. It takes a function as the first argument in purple here, and it applies it to every element in some collection that I have here in green, and then returns a new collection containing these results. So here's an example applying this. You see that if we square 2, we get 4. If we square 3, we get 9, and so on. Usually this kind of thing is more practical to do inline. You don't want to define a separate function for it. In Julia, use the arrow symbol to define an inline function. But what do you do if you have multiple lines of code that you want to inline? Well, then Julia offers this do end form. And what that is it's equivalent to what you see on the left side. Julia will take what's inside the do end form, turns it into an anonymous function, and pass it as the first argument to the function we're calling. So you could do this yourself. If you define a function that takes the function as the first argument, you can tack on this do end at the end, and it will work. So Julia uses this a lot for handling things like opening files and other cases. Another thing you will see in functional languages is partial application. This is a big thing in Haskell. Kind of language is kind of built a bit around this idea. Not quite as smooth in Julia, but still pretty nice. So just to motivate, why do you need a partial application? So imagine that I want to look for what index is the number 6 at. So I provide a function that's like a condition that checks, is the element I'm currently looking at, is it equal to 6? If it is, then we'll return that index. So in this case, it's the third element is 6. So a little note there, Julia has 1-based indexing. So here we're using partial application instead. So we're providing the equals to compare against 6, but we're only giving one argument. And when you do that, Julia will return a function object that asks for the second argument. So this is the function that actually gets passed into find first. And so the second argument is going to be the various numbers in this list. We can do this for other things. So here I'm filtering, give me all the numbers that are larger or equal to 6. Now these things, they don't come automatically. They have to actually be defined. And in the standard library, they are defined for a number of operators, but you could define your own. So here's an example of me defining it for the larger and less than. We'll have to import those functions or operators from the base module in Julia to extend them. What this means will become a bit clearer later. But here I'm defining that if larger than takes one argument, just a y, then we return an anonymous function that takes an x and then compares that x to that y. So we can then use that in our own code. You can see, get me all the values. Oh, find the first value that's larger than 6. That's the fourth value. Or filter, give me all the values that are less than 6. So let's talk a little bit about trade-offs. What is it that makes a dynamic language typically slow? So one of the reasons has to do with what we call boxing and how cache operates. So if you look at a lot of dynamic languages, and this is not limited to dynamic languages, but also statically typed languages that are object-oriented, such as Java, also has this problem. So if you define a class in Java, that is of a type points. Sorry, just a little bit moment. I have to check something. Okay, sorry about that. So if the class is the point class is not final, it could be subclassed. And for that reason, in Java, you would have to store actually what you have to have a tag that stores exactly what kind of type it is. So you can see that there's some overhead in how an object is represented in memory. So you have the actual data you're interested in, the X and the Y in blue, and then you have in gray here, the kind of overhead. You have the type information, maybe a mark or a reference counter, depending on what kind of garbage collection system that you're using. If you use something like Fortran or C or Julia, typically those languages at compilation time will be unboxed. There's no extra kind of bookkeeping stuff on top of the values. You just have the actual values there. Now, why does this matter? Well, you start getting memory fragmentation. So imagine that we have something like a rectangle type, and we have defined the minimum and the maximum extent of this rectangle. In memory, you will see then you will get the data spread out in memory, and there's this little overhead on each one of them. And so you end up fragmenting memory. But if you use a language like C or Go or Julia, you can create this into one contiguous block of memory, as you see on the right side here. And the reason why that matters is because regular main memory is slow, and so you want to put things into cache, and cache can only move things into one contiguous block of memory at a time into cache. So if things aren't sort of like coming right after each other in one contiguous block of memory, then you have to do more reads from main memory and cache. So that just slows things down. So this is also worse when you're dealing with large arrays. In Java, if you have an array of points, unless the type is final, you don't know if you have a subclass that has more members. And so you have to point to somewhere else in memory where the data is actually stored. So each element in the array would be just basically a pointer or a reference to somewhere else in memory. In Julia, you don't have to do that, because if you create a vector in Julia, so that's a one-dimensional array, and you specify, I want an array of points, and I want 3 of them, then Julia knows exactly how much memory that's going to take, because it knows in Julia you cannot, it's not an object-oriented language, you cannot do inheritance of concrete types. You can only implement abstract types. So that means that it knows that point can never take more or less size, and so we can allocate exactly how much memory it needs for each slot. So let's talk a little bit about what makes a dynamic language JIT unfriendly. So I'm going to use a very simple code example here. We define a 2D vector. So if it's not clear what a vector is, I showed a little example here on the corner where you see points are also defined with X and Y, but a vector is more like an arrow. It's a displacement along the X and the Y axis. So often we have operations like multiply that allows us to stretch a vector, make it longer. So it's pretty simple. You just multiply each component with a number. So here's an example. I create a vector with three along the x-axis and 4 along the y-axis. And then we can multiply that, so make it twice as long. Now, what would actually, this is pretty simple. It looks very simple to code, but what actually happens in a dynamic language with this runs? So this is a kind of sort of a pseudocode version based on kind of functions that I know exist in Julia. So this will be a little bit if you were stepping through Julia code in an interpreter or in the debugger, it would look a bit like this. Not entirely. So you can think this is more like maybe a JavaScript or Python or something works. So the first thing we have to do is we have to look up each field. We have to look up the X and the Y. The next is we got to check, are they actually the right type? Are they, say, 64-bit floating point numbers? And then we got to look up our coefficient that we're multiplying. And it could be different kinds of numbers. And typically in dynamic language, under the hood, there'll be something equivalent to a large if else that's trying to deal with each number type in a bit different way. Because at the lowest level, the microprocessor, it has to perform different instructions, whether it's doing a multiplication with an integer or with a floating point number. So it has to figure these things out. That's why I'm showing you that we're doing a conversion, basically an unboxing of the number before we do our computation. So why is it that we have to do all this stuff? Well, the reason is that in a dynamic language, you typically, a field could change its type at any point. So a Y, the Y component could become a string. So we have to check the type every time. Another problem is a field could be gone, it could be removed, or we could add a field. So we have to look up the fields and see if they're actually there. So here's a big important difference in Julia. In Julia, this cannot happen. The language does not allow you to change the type of a field, and it doesn't allow you to remove or add fields. So this is one area where Julia is stricter, and this is a trade-off that had to be made in the language, because if you don't make this trade-off, you cannot get efficient just-in-time compilation, because the just-in-time compiler has to know that the code that it has compiled for a function is going to be valid in the future as well. So this gets us, so that's just kind of touching the surface. So let's talk a bit about what the what the secret sauce is, or what's the key thing in Julia. So I want to begin by talking about the things that are actually not that important, but which people tend to think is very important. So one thing people really home in on is the just-in-time compiler that Julia uses. And the reason it's important to understand that this is not the most important part is because it gives people this false sense that they can just detach the just-in-time compiler from Julia and just stick it into, you know, whatever favorite language that they're using, whether that's Ruby or Python or JavaScript or whatever, and get the same kind of performance. And that will be desirable, right? It means you don't have to learn a new language. You can just, you know, use this awesome new technology. Unfortunately, this is not possible. There is, in fact, nothing very fancy about the Julia just-in-time compiler. If you look at things like V8 or the JavaScript just-in-time compilers or PyPy, these are probably far more sophisticated and large projects that do a lot more kind of hard thinking and analysis to get performance. Yeah, also things like Numba in Python. I'm not an expert in this, but as far as I understand, you decorate individual functions and then you can use LLVM-based JIT compilation. So that's a little bit of what Julia does. It also is based on LLVM, but it's not based on decorating functions in a particular way. So it's a little bit between PyPy and Numba, perhaps, if you're going to try to categorize it. But Julia just-in-time compiler is actually pretty simple. So there isn't very much to gain from anybody else using that. The other thing that I very frequently see is people think, oh, it's all about the type annotations. And the reason people think that is in a lot of languages to avoid this if else, if else, if else, if else thing on type is you add a type annotation. You say, oh, this is always going to be an integer. And now the compiler doesn't have to make all these checks. But in fact, this is not a problem in Julia. You don't need to do type annotations to avoid this because it's not, type annotations in Julia is not used for this purpose. This is very often misunderstood for people that are new to Julia, what type annotations are used for. And so many new Julia developers will often add type annotations to unnecessarily restrict their inputs, thinking it's going to give better performance. Most of the time, it's not going to. So that makes you wonder, well, what is the secret sauce and what are they doing different from everybody else to get this kind of performance? And the simple answer is it's all about language design. Most other languages have tacked on a just-in-time compiler after the fact. You know, Java started on a virtual machine, same with JavaScript. Julia was designed for just-in-time compilation from the very beginning. They knew LLVM existed, and they were going to target that as the one. So if people don't know LLVM, that's a low-level virtual machine. It's been used a lot by Apple for their compiler tool chain for Swift, Objective-C, C, C++, and so on. So it's really just a bytecode representation and lots of modules that can optimize this in different ways. So Julia really just have to produce LLVM bytecode and then optimize that. Well, not only, Julia does its own optimization steps before that, which are kind of the crucial parts. The other thing is it's about programming style and idioms. Julia standard library has been built around these ideas of what can make a language run fast and gives the programmers the kind of tools to do that. And this is pretty important because what you often see is that people that want to try out Julia, maybe they come from Python and they take their existing Python code and they move it over to Julia, and then they just run it and they're like, oh, it runs half as fast. Like Julia isn't depressive at all. The problem with this is that you take code that's written in an idiomatic fashion that makes it maybe fast for Python, but Julia has its own idioms. And very often, the irony here is that Julia code has to be written often in a more straightforward manner. In a lot of slow languages, you try to avoid things like loops. For instance, MATLAB is famous for, and R are famous for that. You are encouraged to, whatever you do, don't use loops if you want performance. Julia is kind of the opposite. You can write loops and there's no performance penalty from that. Well, most likely this actually gives you higher performance. And you also have this thing about you actually want to have pretty small to-the-point functions. So if you have already, in a lot of dynamic languages, you have larger functions that check the input arguments and then do different things. It's generally not what you want to do in Julia. So you have to learn the language to actually get the full benefits here. And the really big thing in Julia that is a kind of novelty that I think it's going to become big in pretty much all other languages in the future is what we call multiple dispatch. So I'm going to try to motivate this with an example. It's kind of silly. It's a bit like the rock, paper, scissors example, except I replaced them with archer, pikeman, and knight. So the idea is that an archer is supposed to be able to beat a pikeman because before the pikeman can get up the hill, the archer has fired his arrow at him. But it's a little bit better for the knight because the knight can charge much faster and get to the archer before he can fire his arrows. So to represent each of these data types, we created these struct series. So we made it simple to just each have a health represented by an integer. And you notice I highlighted the mutable keyword here. And the reason for that is that we want to actually mutate, we want to change the health variable. And to be able to do that, we have to add the mutable keyword. And this is kind of a typical thing in Julia. It's trying to be more functional. So you have to be explicit about when you want to mutate things. So we try to encourage writing using immutable objects. So I'm going to just show you how you would typically want this to work, the code, before I implement it. So we want to be able to create a pikeman and an archer. You might notice I have a semicolon here. This is just to suppress the pretty printing. You only need a semicolon in Julia if you have multiple statements on one line. So we attack an archer with a pikeman, and then we attack the pikeman a second time. And at this point, the health has been lowered enough, and then the pikeman, the archer kills the pikeman. You'll also notice that I have an exclamation mark here, and this is common in Julia. It's a convention in Julia to highlight that this is a mutating function. It mutates it changes the incoming state. So it's not required by the syntax. It's just a convention. You'll find this, I believe, in Ruby, or at least you do that. You do this in Scheme or Lisp programming languages. If we have the archer attack the knight, things don't go as well, and so the knight will kill the archer. So how will we implement this? So we'll have these different functions, and you can see that here we're dealing with the case where we have an archer and a pikeman. But here I changed the types. You can see that I've highlighted these. Here we have an archer and a knight. So the code is a little bit different. We want to give the knight a chance to actually attack the archer. In this case, we have an archer versus an archer. So both of them are firing at each other, and they could potentially both get killed. And then we have the swapped case, where we can just use our existing function for that. And then we have to define what happens when a pikeman attacks a pikeman, and what happens when a pikeman attacks a knight. So what you see here is that we are providing different code for every combination of arguments. It's not like an object-oriented language where you can have a methods that different for each class. Here it's for the combination of arguments. So to explain a bit better how this works under hood, I'm going to use an example here from geometry. You have the same kind of issue here. If you do an intersection between two circles, that algorithm is going to be different than if you're doing an intersection between a circle and a square. So let's start with how it works in a regular, excuse me. So how would it work with a regular object-oriented language like JavaScript or Python? This drawing is actually inspired by the fact that I worked a lot with Objective-C, which actually the object model works very similar to a dynamic language. For these object-oriented languages, we have what we call single dispatch. It's one object decides really what code gets run. So in Julia, you would write something like intersect hexagon, comma shape. But in an object-oriented language, typically the first argument has some special significance. It's the cell for the this, and it decides what code gets run. So we're going to move hexagon outside and do hexagon dot intersect. So what happens is that we look up the class object for the hexagon object, and we find that that's the hexagon class. And on this class, we do a lookup. So we provide basically a string or a symbol that is intersect, and we ask hexagon, okay, where's do you have this a method of this name? And it does typically it does a hash table lookup. If it doesn't find it, it will go to its superclass, which is polygon, and will look, oh, do you have an intersect function? It does have it. And then we will look up, say, an abstract syntax tree. That will be, I think, the Ruby case. Maybe that has changed since I last used it. In Python, that would be most likely bytecode. So this can vary a little bit what exactly you get, but basically you get some implementation that you execute. In a statically typed language, this is a little bit different because at the runtime, classes don't really exist as objects anymore. They've just been collapsed into virtual tables or V tables. So when we're doing just to clarify, so what I mean by static languages here is things like C++ and Java and C#. They do calls in this kind of fashion when you have inheritance hierarchies. So if I'm calling intersect on hexagon, the compiler is going to turn that into some kind of integer offset. So we're just looking at an offset in this table, and then we find a function pointer that points to some machine code that we're running. So this is very fast, right? You're not even doing hash table lookup. It's just a constant lookup. Now we finally get to the Julia case, multiple dispatch. This is very different and also a bit confusing if you're new to this. So there's no special first argument. Every argument is equally significant. So there's no object that we start off. Instead, we go through a table and we find the intersect function. And here's a funny thing. In Julia, functions have methods. This is confusing from an object-oriented perspective, of course, because we're used to methods are on objects. But in Julia, like actually in Common Lisp, functions can have methods. So what the Julia just-in-time compiler will do is it will ask each of the arguments, what type are you? I'm a hexagon. What type are the next argument? I'm a circle. And so we will create a tuple, and it provides this tuple to this method list that exists for every function. So it starts at the top and does a linear search. This is not a hash table lookup. It first asks, is hexagon circle, does it match circle circle? No. Does it match circle square? No. And so on. And it goes down until it gets to the hexagon circle where it has a match. If that entry was not in the list, it will get a match on shape, shape. The reason for this is I haven't shown you that, but we have to assume that hexagon is a subtype of shape. Shape is an abstract type in this case. Anyway, what happens at this point is that you get to an abstract syntax tree. And an abstract syntax tree is basically a in-memory representation of the function when it's been compiled. So we have this tree structure that represents all the function calls and assignments and so on that happens inside a function. And this, in Julia, this works like a template to generate machine code. So you could have, for instance, defined a hexagon and a circle as a parameterized type where you can parameterize whether you're using a floating point or integer or whatever to represent the points. So the abstract syntax tree here would work as a template. So you can feed it, okay, in this case, I'm actually using integers. And so we will use that to generate machine code for this particular case. And once that's been done, that gets cached. So next time this particular function with these same arguments, using say floating points and integers, it will look up exactly the same machine code. And this can never change because if you remember, Julia types can't change. Now, this still would look pretty slow. And the reason for that is that we're doing a linear search, and this is very slow. So languages like that have implemented multiple dispatch typically just do it as kind of a cool add-on. So you can do this in Clojure and Common Lisp, for instance, but it's not what you typically do because it's very slow, right? You're doing a linear search. So if you built a whole language based on multiple dispatch like Julia that was not just in time compiled in the fashion Julia is, it would be a super slow language. So how does Julia get around this? Well, the trick here is that 90% of your code is static kind of observation. So it means that most of the time the code will be compiled to native code. And in these cases, it will find that, for instance, when you're doing, say, this intersect here, the code will be able to, Julia will be able to analyze and find that, oh, this is always a hexagon and a circle. We don't know these particular values, but we know they're always a hexagon and a circle. And when it determines that, it can just put a pointer directly to the machine code. So you're skipping this whole linear lookup, and it's going fast. Okay, so we don't have that much time, but I think I'm going to be able to get through this JIT code generation that gets a little bit more into the details of how this works. So the way we're going to do this is kind of simulate Julia in Julia. So in on a microprocessor, your microprocessor doesn't know types. For a microprocessor, it just pulls values from memory into its CPU registers. And as far as it's concerned, it's just some blobs of data. It doesn't know whether it's an integer or floating point number. So a CPU has to have special instructions for every possible type of arguments that you're using. So there'd be a different instruction for adding, say, 2 integers that are signed than 2 integers that are unsigned. There's a different instruction for adding 2 floating point values and whether they're single precision or double precision. And if you're adding a floating point and an integer, you have to do a conversion. So you have to have a conversion function before you do this performance. So we're trying to simulate that by creating some different functions for different argument types in Julia. The last one that I highlight here, this really funny named function, you can read it as something like vector convert to single precision, convert single, sign integer to single precision double or something like that. Yeah, Intel assembly code instructions have a bit obscure names like that. Of course, we're just implementing these in terms of Julia code. So because the plus operator is already taken in Julia, we're defining our own plus operator with a circle around. This also explains a little bit about the how operators and functions are really just the same thing in Julia. If so we can define this as a function. So you can see that if we're adding 2 integers, then we're calling the add function. If we're having 2 floating point numbers, then we're doing the this vector add function that deals with floating point numbers, and so on. If we're doing an int and a float, we do a conversion to floating point numbers first. That's what I highlighted in purple there, and so on. So how would this look in the REPL environment? So you can call like a regular function like this, but in Julia, there's this simple rule where anything that's a symbol, so it could be a Greek symbol or what you see here, it can use infix notation. So this is equivalent to what you see above. And this explains why the plus operator, the colon thing, and all these kind of stuff in Julia are written in infix, even if they're actually functions. So in Julia, so you can see we can do this in all different kinds of combinations. And here's the cool thing that I really like if you're kind of into low-level stuff. In Julia, you can observe all the different steps that the Julia just-in-time compiler performs. It's what we call a method compiler. It does its compilation, as you saw, per method. That's different from a JIT, tracing JIT compiler, which just takes kind of a stream of instructions that are frequently used and compiles those. Julia does it at method boundaries. So this makes it easier to analyze what's going on at the REPL. So we have this macro called @code_lowered that tells us what this turns into. And when the just-in-time compiler does this compilation, it goes through several steps. So the first thing is lowering, which means it lowers the code to a lower level Julia representation. This then further adds type annotations. Later, we get LLVM bytecode, and then we get native code at the end. And you can inspect all of these steps if you want with these different macros in Julia. So here you can see that Julia has turned this into the add function. And if we continue and we do this with an integer and a floating point number, you can see that it now picks out this conversion function first and this v add s, the single precision double. And you can see this different variants here. So it's really the green part that I want you to focus on. All the other stuff is not that important to know. Now let's contrast this with if we, oh, sorry. I just want to show you that this gives you a list of all the methods that now exist for this function. So we can see dealing with the different argument types. Okay. Now I'm going to show you what happens if we're in regular Julia. What does the actual JIT do? So to be able to observe what happens with the plus operator, it's usually handy to put what you want to analyze inside a function first. So that's what we're doing. So now we do at code native. We're not doing lowering, but we're doing native. We're seeing what kind of native code is produced. And you can see that this produces this integer add function. Actually, in Intel assembly, they're using what's called load effective address. So maybe not that obvious, but it's essentially an integer add. It's maybe a little bit more obvious if we go to the floating point numbers. Then you can see the v add sd that you saw earlier. That's adding two registers, xmm1 and xmm0, and storing the result in xmm0. These are vector registers that deal with floating point numbers. And then we look at dealing with a floating point number and integer, and you can see we get the same thing that Julia produced for us when we were kind of mimicking the just-in-time compiler and looking at the lowering. So this is at the heart of what's happening in Julia, that with this multiple dispatch, you're able to pick specific code for specific cases. And that's exactly what you need for a microprocessor. You want the specific code for each case, and that's what gives you performance. You don't have to do all this if else, if else, if else. You can see here, I didn't type annotate the A and the B, but Julia is able to create a special case for each kind of argument. Okay, I'm going to skip this part. It's not that interesting, but it's just showing that you can add addition for vectors, for instance. We get extra methods in the list. I'm going to show you an example here of actually how powerful the JIT compiler is. So I have these two functions. I have bar that multiplies the input with 2 and then adds to that the input multiplied by 3. And then we have this foo, which is kind of a similar thing, but in a very convoluted way. Let's look at just the first example first. So bar gives me 5, as I would expect. 2 gives 10. Foo, when you use just a single argument, essentially does the same thing. If you have multiple arguments, you can notice at the end there's this sum ys, and so I'm adding up. For every argument, I'm basically doing the equivalent of bar, and then I'm adding up the results. But foo is doing this in a very convoluted way. I'm doing XS, it turns into a list of numbers, and then I'm doing map where I'm iterating over this. I'm providing an anonymous function that's being fed into map, and it's checking at runtime what is the type of X, it's type T, and then it's converting 2 and 3 into this type. And so we get a K and C, and we multiply the X and the X. So it's a very convoluted way of doing a multiply by 5. Now we can look at what bar ends up looking like, and you can see that in LLVM code, this ends up as a single multiply instruction. Now, LLVM does its own neat kind of optimizations. So this it's actually not quite obvious what it does here in native code if you look at it. Because it's this looks like an addition, if you know Intel assembly code. Load effective address is basically for addition, but we were multiplying. So what's going on here? And what actually this, if we spell this out, 2x plus 3 could be turned into 1x plus 4x. And if you know shift operations, you can represent multiples of 2 with shift operations, and the load effective address can do shift operations. So what it does is actually it shifts the content of the RDI register by 4, and then it adds it. And that's the equivalent of multiplying by 5. So you're doing a multiplication very quickly. Some of the rationale for this is that multiplication typically has been very slow on microprocessors. Now let's look at foo with just 7. Despite the fact that this does all this crap that you can see here, it also just turns into 1 instruction. That's quite remarkable because you can imagine that in principle, map doesn't know what kind of function you're passing into it. And in principle, we don't know what the type of X is and so on at the end. And the just-in-time compiler doesn't care. It figures all this out. What about if we do 2 numbers? So we're actually doing all of this on each of number, and then we're adding. In this case, we're just ending up with basically 2 additions. So that is very simple. This requires a little bit more explanation to understand what the just-in-time compiler actually did in this case. So I can try to spell out a bit what it's going on here. So if we take 2 values, Z and W, as input, and then we're applying 2x plus 3x to each of them, that is supposed to give us 2Z plus 3Z as 1 argument, and then 2W plus 3W. And then finally, we're going to be adding this. What the just-in-time compiler does is it basically is able to analyze this and find that first we can simplify it. So we can put the coefficients outside. And then we can do the same trick here and see if we can do change the multiplications to be shifts. And we can simplify further, and we can put the additions of Z and W into an X, and then we do the same thing as we did before. So if you look on the left, you're basically left with the last instruction is the one we had just for bar. So you can see how the just-in-time compiler in Julia can take very dynamic looking code, right? There's no type annotations in there, and yet it's able to figure out that we're using an integer, and it's spreading all through the code and generating this highly optimized machine code. And this gives you maybe some indications of why Julia is actually able to beat many of the top performing statically typed languages in performance once the just-in-time compiler gets going. So to round this off, I want to just show you a couple of one-liners just to show you that it's a pretty expressive language. Here's an example of taking a snake case, how underscore are you, and turning into a camel case. So this starts with, we begin in the inside in the blue, right? And we split this with the split function. We say we want to split on underscore. This gives us an array. And then we call uppercase first. So uppercase the first letter on each of these elements. Now uppercase first only really takes 1 argument, but in Julia you can put a dot at the end of any function, and then that function gets applied to every element if the argument is a collection. And then at the end we can join these together. We can do this same trick by parsing some numbers So say we have a text string with some numbers, we want to turn them into integers. We can split them and then parse and we provide the argument int to say that we want to parse this to integers. Now this does work only on one number at a time, but by using dots, we can work on collections. And then the final thing here is we're destructuring or deconstructing the array that we get back. So we're sort of unrolling or unpacking the array and putting it into the X and the Y and the Z. So you can access the Y here if you want. You have factorial function built in, but you can very easily create that yourself. You can use reduce and you can just pass the multiply here is just a function in Julia like anything else. So like any other function, you can just pass it as an argument. And then we have join, where we're using dot on string. So we apply the string function to every argument, which turns every argument into a string. And then we're joining it with a colon. Now, one thing you saw was that earlier was that there was a lot of some boilerplate in that it's not an object-oriented language, so I couldn't say define a soldier with health and then just do a inheritance to create my archer and my pikeman and my knight and so on. But Julia has a lot of other facilities to get around these kind of limitations. So instead of writing out all these types that are very similar like this, we can use metaprogramming in Julia. So you can create a loop that creates code. So in this case, we're looping over the symbols archer, pikeman, and knight. And then inside here, we have this @eval, which is a macro that we use for creating code in Julia. And this evaluates this kind of code. And in this case, we can provide arguments. So you see the $, which is the same thing we use when we're interpolating strings in Julia. You can use a $, in front of what is a variable to sort of interpolate it into the string, but you can also use that in Julia to interpolate a value into some code that you're defining. So this allows you to create all these different structures. So you can use this for lots of different things. Okay, so we got through this. I'm sorry it took a bit longer than I expected, but we still have some time for discussions or questions. Okay, so I see a hand raised. Claire, let's see. There. Let's see. Claire, let's see if I can, I have to unmute, yes.
I'm afraid that was user error. I was intending to chat and I clicked raise hand instead, so I'll revert that now.
Hold on a little bit, I have to.
Actually, I do have a question.
I just got to get on my headphones so I can hear a bit better. Sorry. Okay, let me see if I can hear you now.
Well, I was intending to type a question in and I must have hit raise hand by mistake. But since I'm talking now, can I ask you the question verbally?
Yeah. Go ahead.
Yeah, apologies if I missed it, but well, first of all, it's an amazing talk, so thank you very much indeed. I was taking screenshots frantically, but
thank you.
Curious to know if you can tell us about any real world cases where you have used this in practice and what the experience was like.
Yeah, so I'm more of like a technology enthusiast, so I'm not a scientist. I'm not really in the sort of the first target audience for Julia. What I have used it for is as a kind of a, maybe I should call it backup language or tool language. So I spent a lot of my time writing code in C++ and Objective-C, and these are kind of verbose languages that you got to write a lot to do very little. So I used Julia a lot for creating tools. So I would actually, I was actually writing code in Julia to generate lots of annoying C++ boilerplate code. And I used it for where you would actually use bash and things like that. I actually used it for compiler scripts. Julia is actually pretty good for integrating with the shell. And what else? I don't use it for image processing. It's kind of sort of like kind of a bit sort of Unixy tools. I use it for code conversion. So like I would take in some C++ code and convert it to something I was interested in. So I kind of used it as a lot of kind of tools, basically. And of course, I played around with these kind of machine learning things because I want to know, what people are actually using it mostly for. I spent some time with the Flux machine coding library. I try to look a bit at, PyTorch, TensorFlow, and so on. So my impression from that is Julia is really amazing language for machine learning. It has some of the design choices in Julia makes it especially very well suited for this. And when I talk to people at Julia conferences, this is kind of what I keep hearing, that people have it really helped a lot of their problems with machine learning. So does that answer your question? Or
it does. It was a really interesting answer. Thank you very much indeed.
Thank you. Okay, let's see. Let's see, was there a Q&A here? Connor, let's see. Oh. Okay, so Richard asks, how much is Julia still evolving? Yeah, there's still a lot happening. We're very excited about this 1.6 release coming out. So one of the challenges for Julia has been that because it's not a tracing compiler, it's a tracing compiler is kind of able to just kick in when there's something that keeps getting repeated. And so you can get kind of things can get going pretty fast. Julia has a little bit of latency. So it normally doesn't matter, but in particular how plotting works, it does matter. So there's this famous like first time to plot in Julia. The first time you plot something in Julia, so like a bar chart or something, it's a bit slow. People don't really like that. And I've been complaining a lot about that. And this is something we're seeing a lot of evolution and improvements in. The other thing is there's been a lot of work to create a Julia interpreter, because that's very handy when you're doing debugging. And one of the last things has also been to get much better threading in Julia. So yeah, there's still a lot of ongoing things, expanding libraries and so on. Okay, and let's see. Connor has a question. Do you know if it's possible for the Julia language to support? Okay, so Connor is having a question, but there's this thing called there's a pipe symbol in Julia. So one complaint, if you saw some of my examples, is that with this very functional style programming, you get everything is nested into each other. If I can, let's see if I can go back a slide to show you what I mean. So if you look at this join uppercase first, right, it's very nested. And that's one of the things that's nice with this kind of object-oriented style is that you can just tack things on the end. You can simulate this with this bar symbol in Julia. Unfortunately, at this point, you can't easily do that if you have multiple arguments. So typically, if you have one single argument in, I can maybe try to show an example of this later, but I'll go on with the next questions here. Okay, so yeah, there's a question here from Ashwin Marshman, I hope I'm saying that correctly, asking who owns Julia. So Julia is open source. It was started at MIT. A lot of MIT guys are involved, and it's, you know, lots of people are involved using it. The people that started Julia did form a corporation called Julia Computing that does a lot of consulting work and helping people out that want to do Julia stuff. And it's a kind of nice source to see the kind of big projects that are being used in Julia, like Celeste and the climate model and so on. But they don't own the language. That's independent. It's just open source. Yeah, thanks everybody for the nice feedback here. Does anyone have any other questions or anything that they want to clarify better? Okay, thanks Jess and Sirkant. Yeah, so Richard asked, the optimization you described looked like they could move into the general LLVM optimization. So of course, some of the things I showed there, like going from LLVM byte code and where they're doing these shifts instead of multiplication, that's all LLVM doing. So Julia, I can't take credit for that. But it's the part going from the Julia code down to the LLVM byte code, that's of course Julia doing. I'm not sure if we could move that into LLVM because it's kind of language specific. I know that one of the issues Julia has is that LLVM, of course, is kind of made for ahead of time compilation and not just in time compilation. So LLVM itself is maybe a bit slow actually for this. So for Julia, it's actually more like Julia would want to maybe have some things done in the LLVM project that facilitates dynamic languages. Yeah, so we have a few more minutes, I guess, if anyone has any questions. Yeah, thanks, Claire. Yeah, this is my first time with this kind of setup, so I realized I should have gotten 2 monitors to deal with this. I get these kind of like sounds, but so are anyone here interested in trying Julia then after this? It's actually pretty easy to install, but of course, there's not many workplaces that are going to sort of require Julia at the moment. So that's why I typically have used it as a kind of second tool for other things that I'm doing. Okay, so I see Ashwin Marsman installed it while they talk. So yeah, it's pretty easy. And if you are interested in getting more serious about it, as I mentioned, I'm having a 4-day online course, 4 hours a day on the 13th of April through 16 North, where I work. You can see, but yeah, so see 60 North here, and my Twitter handle if you want to follow me. I also have a book called Julia for Beginners, and my motivation for talking with this is, right, a lot of people in Julia community are scientists and researchers, and I want to really get this language for more people to use, because I'm not a scientist, and I think it's been a great general purpose language. So the book I've written is kind of meant for everybody. You don't need to be a PhD to read it. I'm trying to have a little bit fun examples with simulating rocket launches or mechanical calculators or any kind of like geeky stuff. Okay, so I guess, well, we do have, yeah, I guess we have 5 more minutes. So I'll hang around a bit here. Let's see. Okay, so it's a question here from Meg. How easy is it to convert code from something like Octave MATLAB to Julia? And I actually have an experience with this. The company I worked for, we're doing oil exploration. So we're doing analysis of what we call synthetic seismograms. And not being a scientist, I didn't know how to do that. We had a scientist that wrote this code in MATLAB, and we had to get this into our software and try it out. And I actually took just that MATLAB code and pasted it into my Julia editor. And I only had to do a few modifications actually to get it to work. Like in Julia, you have to specify the, you have to create the matrices before you use them. In MATLAB, you can just start using them right away. So that was kind of the main difference that I remember. Apart from that, it was actually a lot of similar, as long as you have a pretty simple MATLAB code, it's actually pretty similar. Yeah, so yeah, for MATLAB, it's an R. It's probably easier to convert to Julia because they are the one-based indexing. You have to take a little bit more care probably if you're going from Python to Julia because they're the zero-based to one-based indexing. Okay. Thank you everyone for attending. And I'll probably hang out in the Remo thing after I take a little bit break. So maybe I'll see you later. Okay, thank you. I'll stop sharing now.